So in general, for this new, as far as this attempt at acceleration with the V actually breaks into the two parts. So the V has this V part acceleration, which I'm going to label acceleration. As far as this is due to an actual acceleration that actually takes place. And this other V is I'm going to call violation. This is like the V in the water glass. In the water glass, the V is actually entirely violation. So this is V's that are trying to go down to the bottom of the water glass that can't take place. It's a V violation. So this contributes to U vector at the next time step. But this guy is cancelled by the gradient of pressure. So writing this out in terms of W, so W equals U vector at T. The way I defined it, will U vector at T plus V, so writing this all the way out, V vector acceleration plus V vector violation. And then I'm basically defining, this kind of by definition, U vector at T plus delta T is going to equal the U vector at T plus the V vector acceleration. So this part is the permitted part. And then what that means is, since the gradient of U vector has to equal 0, the gradient of this also has to equal 0. And what that means is if I take, not the gradient, but since the divergence of the U vector equals 0 at the next time step, the divergence of this will also equal 0. So taking the divergence of W, this divergence is going to equal 0, so the entire divergence of W actually comes from the violation term. And as discussed with the glass of water, it turns out the violation has to be counterdicted. And what stops the violation is going to be the gradient of pressure. So the violation equals the gradient of pressure. So putting these two things together ultimately comes up with the equation that the divergence of W equals the divergence of the gradient of pressure. And then, except I also have some constants in here, there's also a delta T over rho. With these constants, delta T over rho. And I'll multiply it out. So this, it can be, so since W can be computed, as far as W can be computed for each time step, this almost gives enough information to solve for the gradient of pressure. And if the gradient of pressure could be solved for, then violation can be computed, and the violation, being now the gradient of pressure, can just be subtracted from W to get the new velocity at the end of the time step. So that's the general principle. However, this equation in itself will not uniquely compute the gradient of pressure. There actually needs to be boundary conditions. And the boundary conditions are basically these. So V vector at a boundary. Computer is slowing up. Okay. Of the acceleration, tangent, by which I mean basically tangent to the boundary. So this would be in the water glass, the tangent acceleration would be trying to go down through the bottom of the glass, or trying to go sideways. That would be a tangent velocity. So the tangent has to equal 0. And also, of course, the u vector tangent at any time has to equal 0. So since the u vector tangent at any time equals 0, that means u of t, which is part of the computation for w, equals 0. So the w vector tangent is going to equal 0. No, actually, it's not going to equal 0. What it's going to equal is it's going to equal entirely the violation. The w vector tangent equals v vector violation. Anything that is trying to go through a wall is going to have to be countered. And so, so the only thing that can be allowed tangent to the surface is the part that's going to get cancelled out, which is the violation. Otherwise, the fluid would be trying to go through a wall. So that basically means that the w vector tangent at the boundary is going to equal the gradient of p tangent at boundary or wall. So writing this out specifically using the box, since this is all going to be a box, this means Wx evaluated at, for instance, x equals 0, or any boundary condition, is going to equal the constants again, which is now t over rho, whatever. And then this is going to be the change in the pressure across the boundary, which is dp dx. And this is of course evaluated at x equals 0. And wy is going to equal, evaluated at y equals 0. Same basic idea, delta t over rho. And then the pressure Ey, this time evaluated at y equals 0. So it turns out these equations plus the equation that we had earlier, which is the divergence of w times the divergence of the gradient of p, these things together can actually be solved to find the gradient of p. So this and equals these equations. Taking these equations together can basically be used to solve for the gradient of p, and as it will be shown, that in turn can be used to solve for the u in the next time that it grabs. So these for gradient of p and gradient of p and w vector minus gradient of p. Make sure I got that right. Yeah, that's going to be the new velocity. So w vector minus gradient of p is going to equal the velocity at the new time step. So that's basically that. I'm just going to box these things. Okay, so the next video will go over this as an example, some examples to see how detailed how this works.